it is advisable to request an amendment to the 2004 Chicago Electrical Code to permit the utilization of nonmetallic conduit for the segment of the service entrance conduit situated between the meter and the main disconnect. Nonmetallic conduit, encompassing materials like polyvinyl chloride PVC or high-density polyethylene HDPE, furnishes ample safeguarding for service entrance conductors and is prevalent in diverse jurisdictions. The primary bonding jumper, which establishes a connection between the service grounded conductor and the equipment grounding conductor or conductors, necessitates installation at the main disconnect. Should nonmetallic conduit be disallowed in this particular segment, adherence to this stipulation becomes challenging. The majority of standard meter cans are equipped with neutral lugs bonded to the can. This implies that the service grounded conductor is already efficiently bonded to the service equipment. Sanctioning nonmetallic conduit in this segment would ensure uniformity and mitigate potential ambiguity. Nonmetallic conduit generally incurs lower expenses compared to metallic conduit, potentially yielding cost reductions for building proprietors. A proposed amendment involves revising Section 18.27 230.43 to stipulate that service entrance conductors must be installed in accordance with the pertinent requisites of the chapter governing the wiring method employed, restricted to the subsequent methods: firstly, rigid metal conduit; secondly, intermediate metal conduit; thirdly, service entrance cables for pre-existing residential occupancies comprising a maximum of 3 units; fourthly, busways; fifthly, cable bus; sixthly, mineral insulated metal sheath cable; and seventhly, nonmetallic conduit for the segment between the meter and the main disconnect. This amendment would specifically permit the utilization of nonmetallic conduit within the segment of the service entrance conduit spanning from the meter to the main disconnect, while upholding the prohibition on its application for the entirety of the service entrance conduit. Nonmetallic conduits, such as PVC and HDPE conduits, are frequently employed in electrical installations. PVC conduit, known as polyvinyl chloride conduit, stands out as a lightweight, rigid plastic conduit extensively utilized for safeguarding and routing electrical wiring. Its merits encompass cost-effectiveness, ease of installation, and resistance to corrosion. It is typically available in 10-foot sections and joined via couplings and solvent cement. PVC conduit is suitable for encasing electrical conductors in walls, floors, and ceilings. It is also appropriate for direct burial applications. However, it is crucial to recognize that PVC conduit exhibits temperature limitations. It should not be employed in environments where temperatures surpass its maximum rated value, typically around 167 degrees Fahrenheit or 75 degrees Celsius. Furthermore, it is essential to adhere to local electrical codes and regulations concerning its proper installation and utilization. HDPE conduit, short for high-density polyethylene conduit, constitutes a flexible plastic conduit frequently employed in underground electrical installations. Its resilience to chemicals, moisture, and corrosion renders it well suited for direct burial applications. HDPE conduit is commonly employed for encasing electrical, telecommunications, and data cables underground. Its adaptability enables it to navigate bends and curves with relative ease, diminishing the necessity for multiple fittings. Moreover, HDPE conduit exhibits exceptional durability and resistance to impact, thereby furnishing robust safeguarding for the cables it houses. It is imperative to adhere to local electrical codes and regulations pertaining to its proper installation and utilization. When contemplating the application of nonmetallic conduit, factors such as cost, installation requisites, and environmental conditions necessitate meticulous evaluation to ascertain the optimal material for the intended use. The National Electrical Code (NEC) outlines specific guidelines for the utilization of nonmetallic conduit, encompassing PVC and HDPE conduits, in various applications. Article 352 of the 2023 NEC addresses requirements for rigid polyvinyl chloride conduit, while Article 353 focuses on high-density polyethylene conduit. Some key points include: firstly, permitted uses. The NEC delineates the specific applications where PVC and HDPE conduits are permitted. These may encompass underground installations, encasement in concrete, and exposure to corrosive environments. It is essential to consult the NEC to ascertain the permissible uses for each type of conduit. Secondly, installation. The NEC provides comprehensive instructions for installing PVC and HDPE conduits. These guidelines encompass aspects such as support spacing, securing methods, and bending radii. Adherence to these installation practices ensures the structural integrity and safety of the conduit system. Thirdly, opacity. The NEC addresses the opacity of conductors installed within PVC and HDPE conduits. Opacity refers to the current carrying capacity of a conductor. The NEC provides tables and calculations to determine the appropriate conductor size based on the conduit type, ambient temperature, and the number of conductors within the conduit. Fourthly, grounding. The NEC mandates proper grounding and bonding procedures for electrical systems utilizing PVC and HDPE conduits. Grounding ensures a safe path for fault currents, minimizing the risk of electrical shock. The NEC outlines the requirements for grounding conductors, bonding jumpers, and equipment grounding. Fifthly, temperature limitations. The NEC specifies temperature limitations for PVC and HDPE conduits. These conduits may not be suitable for applications where temperatures exceed their maximum rated values. It is crucial to select conduit materials that can withstand the anticipated operating temperatures. Sixthly, markings. The NEC necessitates that PVC and HDPE conduits be clearly marked with pertinent information, such as the manufacturer's name, conduit size, and applicable standards. These markings facilitate identification and ensure compliance with regulatory requirements. It is imperative to consult the latest edition of the NEC and local electrical codes for comprehensive guidance on the utilization of non-metallic conduits. Compliance with these standards ensures the safety and reliability of electrical installations. Several potential advantages accrue from permitting the utilization of non-metallic conduit, specifically between the meter and the main disconnect. Firstly, enhanced safety. Non-metallic conduit inherently provides a double insulated system, thereby augmenting safety by mitigating the risk of electrical shock. Secondly, diminished corrosion. Non-metallic conduit exhibits remarkable resistance to corrosion, rendering it particularly well suited for installations in damp or corrosive settings. Thirdly, weight reduction. Non-metallic conduit typically weighs less than its metallic counterparts, facilitating easier handling and installation. Fourthly, cost-effectiveness. Non-metallic conduit generally entails lower material expenses compared to metallic conduit, potentially resulting in cost savings. Fifthly, installation simplicity. Non-metallic conduit is generally easier to cut, bend, and assemble in comparison to metallic conduit, thereby diminishing labor expenses and installation duration. However, it is crucial to acknowledge potential drawbacks. Firstly, restrictive mechanical protection. Non-metallic conduit may not afford the same degree of mechanical protection as metallic conduit, rendering it potentially susceptible to damage in areas prone to physical impact. Secondly, flammability considerations. Certain non-metallic conduits may exhibit flammability, necessitating adherence to fire safety regulations and appropriate installation practices. Thirdly, grounding requisites. Specific grounding practices may need to be adhered to when employing non-metallic conduit to ensure the integrity of the electrical system. The decision to permit non-metallic conduit between the meter and the main disconnect should be predicated upon a comprehensive assessment of these advantages and disadvantages, alongside meticulous consideration of local electrical codes and regulations. Article 250.28 of the National Electrical Code NEC pertains to the main bonding jumper and its installation requirements. The main bonding jumper is a critical component in an electrical system that ensures a lower impedance path for fault current, thereby facilitating the operation of overcurrent protective devices and minimizing the risk of electrical shock. Some key aspects of Article 250.28 include: firstly, location. The main bonding jumper must be located at the service equipment or the source of a separately derived system. The service equipment typically refers to the main service disconnect enclosure, while a separately derived system includes generators and transformers. Secondly, connection point. The main bonding jumper connects the grounded conductor, typically the neutral conductor, to the equipment grounding conductor or conductors. This connection establishes a common reference point for grounding and bonding within the electrical system. Thirdly, sizing. The NEC provides specific sizing requirements for the main bonding jumper based on the size of the service entrance conductors. The size of the bonding jumper must be adequate to safely carry the maximum available fault current. Fourthly, material. The main bonding jumper must be made of copper or other corrosion-resistant material. The material must be suitable for the environmental conditions and capable of withstanding the stresses associated with fault currents. Fifthly, installation. The main bonding jumper must be installed in a manner that ensures a reliable and permanent connection. It must be securely fastened and protected from physical damage. The connection must be accessible for inspection and maintenance. Sixthly, accessibility. The main bonding jumper must be accessible for inspection and maintenance. It should not be obstructed or concealed in a manner that would prevent access. Seventhly, identification. The main bonding jumper must be identified with a green color or by other approved means. This identification helps to distinguish it from other conductors in the electrical system. It is essential to consult the latest edition of the NEC and local electrical codes for detailed guidance on the installation and requirements of the main bonding jumper. Compliance with these standards ensures the safety and reliability of electrical systems. When a standard meter can is equipped with neutral lugs bonded to the can, it implies that the neutral conductor is electrically connected to the metal enclosure of the meter can. This bonding serves several purposes. Firstly, grounding. The bonding of the neutral conductor to the meter can provide a path for fault current to flow back to the source in the event of a ground fault. This helps to quickly trip over current protective devices such as circuit breakers or fuses, thereby minimizing the risk of electrical shock and equipment damage. Secondly, voltage stabilization. The bonding of the neutral conductor to the meter can help to stabilize the voltage on the neutral conductor. This can improve the performance of sensitive electronic equipment and reduce the risk of voltage fluctuations. Thirdly, noise reduction. The bonding of the neutral conductor to the meter can help to reduce electrical noise in the system. This can improve the performance of sensitive electronic equipment and reduce the risk of interference. The bonding of the neutral conductor to the meter can is typically achieved by means of a bonding screw or strap that connects the neutral lug to the metal enclosure. The bonding connection must be made in accordance with the National Electrical Code (NEC) and local electrical codes. It is important to ensure that the bonding connection is properly installed and maintained to ensure the safety and reliability of the electrical system. The service entrance conductors are the wires that run from the utility company's transformer or service drop to the main disconnect in a building or structure. These conductors are responsible for carrying the entire electrical load of the building and must be installed in accordance with the National Electrical Code (NEC) and local electrical codes. Here are some key aspects of service entrance conductors. Firstly, conductor size. The size of the service entrance conductors must be determined based on the calculated load of the building. The NEC provides tables and calculations to determine the appropriate conductor size based on the type of building, the size of the building, and the electrical loads that will be connected. Secondly, conductor type. Service entrance conductors can be made of copper or aluminum. Copper conductors are more expensive but have a higher conductivity than aluminum conductors. Aluminum conductors are less expensive but require larger sizes to carry the same amount of current as copper conductors. Thirdly, insulation. Service entrance conductors must be insulated to prevent electrical shock and short circuits. The insulation must be rated for the voltage and temperature of the conductors. Fourthly, overcurrent protection. Service entrance conductors must be protected by overcurrent protective devices, such as circuit breakers or fuses. The overcurrent protection must be sized to protect the conductors from overload and short circuits. Fifthly, grounding. Service entrance conductors must be properly grounded to provide a path for fault current to flow back to the source in the event of a ground fault. The grounding system must be installed in accordance with the NEC and local electrical codes. Sixthly, installation methods. Service entrance conductors can be installed in a variety of ways, including in conduit, in cable trays, or direct buried. The installation method must be appropriate for the type of conductors and the environmental conditions. Seventhly, clearances. Service entrance conductors must maintain proper clearances from buildings, structures, and other objects. The clearances must be in accordance with the NEC and local electrical codes. It is essential to consult the latest edition of the NEC and local electrical codes for detailed guidance on the installation and requirements of service entrance conductors. Compliance with these standards ensures the safety and reliability of electrical systems. When considering the use of non-metallic conduit for the service entrance, several factors must be taken into account. Firstly, local codes and regulations. It is imperative to consult local electrical codes and regulations to determine whether non-metallic conduit is permitted for service entrance applications. Some jurisdictions may restrict or prohibit the use of non-metallic conduit for this purpose. Secondly, environmental conditions. The environmental conditions at the installation site should be assessed. Non-metallic conduit may not be suitable for use in areas subject to extreme temperatures, corrosive substances, or physical damage. Thirdly, conductor size and type. The size and type of service entrance conductors must be considered. Non-metallic conduit must be sized appropriately to accommodate the conductors and provide adequate protection. Fourthly, mechanical protection. A level of mechanical protection afforded by non-metallic conduit should be evaluated. If the service entrance is susceptible to physical damage, metallic conduit may be a more suitable option. Fifthly, grounding requirements. The grounding requirements for the service entrance must be carefully considered. Non-metallic conduit does not provide a grounding path, so a separate grounding conductor must be installed. Sixthly, fire resistance. The fire resistance of non-metallic conduit should be assessed, particularly in areas where fire safety is a concern. Some non-metallic conduits may be more fire resistant than others. Seventhly, cost considerations. The cost of non-metallic conduit should be compared to the cost of metallic conduit. Non-metallic conduit is generally less expensive than metallic conduit, but the overall cost may vary depending on the specific application. It is essential to weigh these factors carefully before deciding whether to use non-metallic conduit for the service entrance. Consulting with a qualified electrician or electrical engineer can provide valuable insights and ensure compliance with all applicable codes and regulations.